Alright, friction, more practice. So let's read the problem. As represented in the diagram below, a constant 15 newton force. So you have an applied force of 15 newtons. Fa is applied. And the mass is 2.5 kg. Accelerating the box to the right at 2 meters per second squared. And the question wants you to figure out, well, what is my net force? What is my net force? Net force is what? Well, you also learned in class that F net is ma. That's Newton's second law. 2.5 times 2 is 5. And so you have an F net of 5. You just solve for A. B. Well, determine the magnitude of the force of friction on the box. Well, your magnitude of the force of friction. Well, let's take a look at a free body diagram, right? We know that, well, if the block is in motion, there's an applied force this way. Well, if we know the block is in motion and it's across a surface, we also across the surface, we also know there's a frictional force. We know there's a frictional force here. And we know by definition, F net is the sum of all forces acting in a direction. And so we know that F net is equal to Fa plus Ff, the sum of all forces acting in one direction. Well, now Fa, your applied force, we know what that is. Well, we also know what our net force is. We know our net force is 5. We know our applied force is 15. The question wants you to figure out, well, what is my frictional force? Minus 15, minus 15, minus 10. And that is our frictional force, negative 10 newtons. Well, it's asking you for the magnitude of force of friction, so it's just 10 newtons, because they only want magnitude. But it's good to get used to using your negative signs. What is the coefficient of kinetic friction between the box and the surface? Well, if we know our frictional force is negative 10 newtons, and we know that frictional force is mu times Fn, negative 10. We don't know what mu is, and we talked about this if the box is not moving up or down. Not moving up or down, we know that Fn is equal to negative Fg. So we're going to substitute Fn, negative Fg. So negative Fg is negative m a, and we know that mass is 2.5, negative 2.5, and my acceleration due to gravity is negative 9.8. Negative 2.5 times negative 9.8, 19.6, and then 21.5, I think it is. I think it's somewhere around 21.5 U, 1.5 U, then divided by 21.5, 21.5, and so we get a U mu of something. 10 divided by 21.5. Somewhere around this. Now, if you follow through with all your signs, you're going to get a negative number. But coefficients cannot be negative, so you just ignore that negative number right there, okay? So you ignore that negative number. But as long as you follow through your signs here, you should all be fine. You should be fine, regardless. Now, that's how you solve that question. 3. A 5 kilogram box, so you have mass is 5 kg. Box is acted upon by a force of 27 newtons east. So your applied force is 27 newtons east. And your frictional force is 17 newtons west. What is the magnitude of acceleration of the box? And what is the acceleration? Well, again, we know that F net is ma. And we know the sum of all forces acting in your x direction, and if it makes it easier for you, that's your frictional force, and that's your applied force. Well, the sum of all forces acting in one direction are just your applied force and your frictional force. Well, what's my applied force? 27 newtons east, so it's a positive. My frictional force is 17 newtons west, so it's negative. And my mass is 5. And what's my acceleration? So I'll finish solving for this. And you get an acceleration of 2 meters per second squared. So the answer is B. Number 4. A rubber block weighing 60 newtons. So that's your force through gravity, right? We know that force through gravity is our weight. They're synonymous. Is resting on a horizontal surface of dry asphalt. What is the magnitude of the minimum force needed to start the rubber block moving across the dry asphalt? So they want to know the minimum force required, which means they want to know what is the maximum static frictional force that the block has, right? So again, if we draw a free body diagram, force applied and force due to friction. Well, we know that the friction, if it's not moving, it's friction. It's a static friction. And so we know our mu, and that's what kind of surface is this. Rubber on dry asphalt. Rubber on dry asphalt is 0.67. So what is the minimum force we needed to start the rubber block moving across the dry surface? Well, we want to know what our frictional force is. You know our frictional force formula, also on your reference table, is that. And we want to know what our Fn is. Well, lucky for us. Lucky for us. We also know that if an object is not moving down or up, we know that F net in the y direction is 0, and the sum of all forces in our y direction is Fn plus Fg, 0. Fn is equal to negative Fg. So we know our Fn is going to be equal to our force due to gravity. So we're going to plug this all in. Ff is equal to mu is equal to 0.67. So if you're confused about how I got this number, here it is. 60 over here. We know Fn is negative 60 because over here. So we put negative 60. 0.67 times negative 60 is somewhere around negative 40, somewhere around there. And that's our frictional force. Was that one of the answers? Yes, it is. It is D. It is D. 5. Which arrow best represents the direction in which friction acts on the ball at point P? Well, if the direction of the motion of the object is going that way, we know that friction is the opposite direction of motion. So this is your force through friction that way. So it's B. Remember, it's opposite. Opposite. 6 was the 12 Newton horizontal force. So your applied force is 12 Newtons. Box remains at rest. Force of static friction acting on a box is what? This is a concept question, which means that you know that, well, your static frictional force is always equal to your applied force, your maximum static frictional force, which means that if I apply a force of 12 newtons and it doesn't move, well, then there must be a frictional force of 12 newtons back here. And again, if I apply a force of 20 newtons here, 20 newtons to the box to the right, and it's not moving as well, then it also means that my static frictional force acting in the opposite direction is also 20 newtons. Also 20 newtons. Alright. 12 newton horizontal force. Well, if it wasn't applied in when I discussed it, the answer is C. The answer is C. That wasn't clear enough. 7. Diagram shows a mass of 4 kilograms acting on the block, acceleration 10 meters per second. It's a weird M, but hey, we're not all perfect. What's the magnitude of frictional force acting on the block? So what is that? What they want to know what that is. So let's look at this. What's magnitude? Well, all we're gonna do right now is set up our equation. And we know the sum of all forces acting in our x direction, again labeled in diagram, is Fa plus Ff. Right? That's the sum of all forces acting in our direction, one direction. And we know the mass is 4, and we know acceleration is 10. Let's substitute even further. We know our applied force is 50 newtons, because it says so in the diagram. Subtract 50, get rid of that 50, and you get negative 10 newtons. What's the magnitude? So they only want the number, right? They only want the number, the magnitude. So they want 10 newtons, and 10 newtons is the answer, is B. Answer is B. 8. The force required to start an object sliding is larger than the force required to keep the object sliding at a constant velocity. The magnitudes of required force are different in these situations because the force of kinetic friction is less. It's literally in the problem. They say that the friction required, the force required to keep the object sliding at a constant velocity is lower than the force required to start the object from rest. Because, well, if I apply a force of 20 newtons that way, and I get it, and I don't get it moving, there's a static frictional force of also 20 newtons back. But let's say I apply a force of 20.1 newtons to get it, and it finally starts moving. Well, then kinetic friction starts taking place. And the kinetic friction is much less. Let's actually make this, well, it's not much less. It is less, though. It is less. And so let's make this arrow like that. And let's say the kinetic friction is 18 newtons. And so once it's already moving, I can just drop my force down to 19 newtons, and it can still move because it's already moving. It's kinetic friction. It can still move. And so I don't need as much force anymore to keep it moving. Because my kinetic friction is always less than my static friction. All right, ask me any questions if you have any questions.